Hey guys, welcome. Yeah, so I hope everyone is doing well. And this will be the last video I'll make in preparation for the 2020 AP Calculus BC exam. And this is what you'll find in this video. FYI, I've already made 3 videos to help you review, so check out those videos. But yeah, what you'll find in this video are, in order, first, basically the latest update and information on the AP exam, what is allowed, what's not allowed, when will it be, and yada yada. And then there are sample questions that the AP has released. Saying sample questions is a little hyperbolic. It's actually one sample question and information about what the second question would look like. Remember, there are only going to be 2 questions this year, right? Okay, and then there is going to be one question that I elected or selected from the 2016 AP Calculus BC FRQ, which will review particle motion as a vector, right? So I have a video on particle motion where the position function is given as a polynomial, and therefore the velocity and acceleration functions are also polynomials. But the example I'll give here will be one where the position is given as a vector, right? Okay, so it'll be different from that, obviously, and that's why I'm making a video on it. And then at the end, towards the tail end, I want to make a minor correction on one of the earlier videos that I made, on one of the earlier review videos I made. So this is what to look out for. Now, I'll leave a link to where I found all this information, and so you could, if you want, take your time and learn more from the link, because, well, that's where I learned all this stuff. First thing first, these are kind of some of the times on when the AP exam will be given this year. And then this is what to have ready on exam day. Feel free to pause and read more carefully. And yeah, and next is what is permitted on the test. So these are the things that are allowed on the test, right? And what is next? Let's see. So yeah, there are going to be 2 questions. One of them you'll have 30 minutes for, and it's really 25 minutes long, but if you want to know why I said 30 minutes, well, again, follow the link and read more. But yeah, this actually, they provided a sample question for, so we're going to go through that sample question. You'll see that most of the sample question is actually something that you already saw from my 2019 FRQ solutions. They only modified one little bit of questions from the 2019 FRQ and sample question 1. And then the second question is 15 minutes long, but there's, again, a 5-minute cushion. So you have, what, 30 plus 20, so that's 50 minutes total. And the breakdown was the first question is 60%, and then this is 40%, right? Again, feel free to pause and read, or learn more at the link that I'll provide you. And what's covered, I've already gone through what's covered in an earlier review video. And so look at that for, details of what is covered, but here are the topics that are covered. And so let's look at sample question 1 then, without delay. All right, now this question is identical to a question from the 2019 FRQ, so poor of them if you ask me that they don't provide you anything new, but it is what it is, right? And so an extension of sample question 1, so this is still a part of sample question 1, brings to light something new. That is actually this. This, again, is a question that we've seen on the 2019 FRQ, so check that out. But what was I going to say, 2019-18? But anyway, I almost misspoke. But whatever, I'm like trying to save myself some blushes. Okay, so the last part G, is, the one that's new, and so this is the only one worth going over. And so here it is. I'll show you how to solve this part G. So they say evaluate this, where p is greater than 0. Now, this is clearly an improper integral, and we know we have to use proper grammar on improper integrals, so the first thing you should write is limit as a goes to infinity, and then 1 to a, and again, this is because we can't plug in infinity. Infinity is not a number. And then you could write x to the power negative p plus 1. Now, notice that this here, right, is a number that is more than -1. Why? Well, it's less than -1. It's not more than -1. It's like an actual value, but it's more than -1 in absolute value. Why, you ask? Because they said that p is greater than 0. So if, say, p is equal to like 0.1 even, like a very small value, then this says x to the -1.1, right? Okay, so that's worth mentioning. Otherwise, moving forward, we know how to integrate things like these. It's just simple power rules. So we're going to go lim is a goes to infinity, and then what is it going to say? Lim is a goes to infinity, and then it's going to be, well, this here is really x to the power -p, and then -1 if we distribute that minus sign. So what we do to integrate is we add 1 to the power, and then we divide by this new exponent, right? So, I didn't have my ruler ready. It's okay, you'll live. Alright, so here it is. By that I meant I should have kept it horizontal. So we divide by this new power. Notice that this new power simplifies because -1 plus 1 is just 0. So what we're dividing by really is -p. Although, yeah, we're really dividing by -p minus 1 plus 1, which again simplifies to that. Okay, so we've just finished integrating. So what we could do is evaluate, right? And then we could take the limit. Okay, so the evaluation will mean that we draw a vertical line here and write 1 at the bottom and then a at the top, right? So from here we go, this is the same as limit is a goes to infinity, and then what? Limit is a goes to infinity, and so plugging in a, we're going to get a to the minus p. Again, this exponent just simplifies to minus p, divided by, I'm not going to use a ruler, I don't want to be that annoying, divided by minus p, right? Okay, and again, minus p is maybe a very small number, but it's still like a negative number because p is greater than 0, right? Okay, and then we'll have minus, but then there's a minus p downstairs on what I'm about to write. So this is really a plus, which means that I write just over simply positive p, right? And what goes in the numerator is going to be, well, 1 to the minus p, right? Okay, cool. So 1 to any power is just 1. We reckon that. So we go, all right, this is the same as limit is a goes to infinity of what? Of, well, a to the minus p. Since we know that this is a negative number, we could put downstairs, right? So we could be like 1 over, and then it's going to be minus p, and then a to the power of p, right? And then otherwise, we'll have plus 1 over p, right? Okay, now, as a goes to infinity, right? No matter how small p is, this denominator is going to grow without bound. And so this whole thing is going to go to 0, which means that after evaluating the limit, what we're going to find is 1 over p. Well, fine. So 1 over p is a finite number, and therefore we see that this integral converges, but the question isn't convergence. We just had to find the value, so there that is. Yeah? Okay, cool. Cool. So I'm like having a torrid day with speaking English. All right. So we're ready to move forward. All right. So what is next? Well, I've already told you at the start the things to look out for. Again, very annoying of them if you ask me that. First of all, they don't give you a novel like practice question 1. And or sample question 1, and then the only thing they provide about question 2 is like this bit of information. I'm not gonna read it to you. Hopefully you can read, and so sorry. And so take the time to read it. All right. But otherwise, this is the promised question about particle motion from the 2016 BC FRQ, and this is problem 2 on there. And this is where particle motion is given as a vector. They're kind of being careless here, writing it in like parenthetical fashion. It's really like vector fashion that it should be written, but they mean vectors, and so you should know that. So like, I'm saying vectors have like these harder brackets with sharp turns and stuff. Okay, we'll live. All right, so what they said is that dx dt is here, and like it's this function, and this is a calculator active question, and so you need a calculator to do some parts of this question. I'll leave the calculator portions to you. I'm just going to walk you through how to solve each part. And they said that y of t is a function displayed here, yeah? Okay, so also they told us that at time t equals 0, the particle has position 5 comma 1. Yeah? Okay, cool, cool. So part A says, find the position of the particle at time t equals 3. Okay, so first of all, let's find the x coordinate of the position of the particle at time t equals 3. That'd mean that we figure out what x of 3 is. Now, anytime that you want to do something like this, which is given the derivative, you want to go back and find a specific value. Once you're given an initial value, what you should do is try and use the evaluation theorem. It's correctly called the evaluation theorem, but in some corners called the fundamental theorem of calculus part 2, and that is right that this is the same as the integral from 0 to 3 of, well, dx, which would be, right, dx, which would translate to x of 3 minus x of 0 is equal to, I don't like that x. I'm like really annoying about handwriting. My bad, y'all. So that's better. I feel better already. Okay, so this is equal to what? 0 to 3, and then what? And then, dx is going to be t squared plus sine of 3t squared dt. So t squared plus sine of 3t squared and then dt, right? Okay, cool. All right, so now you'll need a calculator to figure out what this integral is. As I said, this is from the calculator portion, as it is question 2 on the 2016 FRQ. And so I don't have a calculator handy to tell you what this is, but we're told that x of 0, the position of the particle at time t equals 0, its x coordinate anyway, is 5. So we replace this with 5. And what we're seeking is x of 3. So it's clear that in this equation, all I have to do is add 5 over to the right side, and we are done. We'd be able to find x of 3. So I get rid of this minus 5, right? Write a plus 5 outside of the integral on the right-hand side, and then slide this so that you don't feel bad and I don't feel bad. And then there it is. And we are done. Yeah? Okay, well, at least for the x coordinate. What we need to get to is x of 3 comma y of 3, right? It turns out the y of 3 is very simple. X of 3 is this number again. You need to finish the integral part in your calculator. Just type it into your calculator and you'll say, you'll claim that to be this. Now, y of 3, well, since this is the y of t function, we just look at t equals 3 and we could see that y of 3 is negative a half. You could more carefully calculate this equation of this line and plug in 3 into it, but you really don't need to do that. If you have eyes, you can tell that it's negative 1/2, right? So we have x of 3 comma negative 1/2, where again x of 3 is what is over here. Yeah? Okay, cool. So that finishes part A. All right, so then part B, on to part B. All right, so for that, right, read, and I'll catch up. It says, find the slope of the line tangent to the path of the particle at t equals 3. All right, so we know, we've been through this. I'm going to write in a different color to keep it interesting. So we know that the slope of the tangent line is always dy dx, right? But notice then dy dx should be, I guess I'll do this part in red. So dx, well, no, sorry. It would be dy dt, right? Divided by dy dt divided by dx dt. And we want to evaluate this at t equals 3, so we could individually evaluate the numerator and the denominator at t equals 3. So this at t equals 3, and then this at t equals 3, right? Clearly, if you simplify dy dt over dx dt, it simplifies to dy dx, right? And so what we're saying is doing the right-hand side at t equals 3 amounts to figuring out dy dx at t equals 3, which is the task at hand, right? Okay, cool, cool. So dy dt at t equals 3, right? Since we have y of t here, that's really like saying y prime of 3, right? And then the denominator that we have is really saying x prime of 3, right? Okay, cool. Okay, so the denominator is x prime of 3. Got it. Okay, so for y prime of 3, we could look at y and see that y prime of 3 is, we didn't do that part. Y prime of 3 is going to be the slope of this line, right? Because it's a single line segment from t equals 2 to t equals 4. So rise over 1 would mean 1 over 2 So the numerator is 1/2, and then the denominator is, since as I've pointed out here, dx dt means x prime, we just plug in 3 in here. So that would mean 3 squared, which is 9, plus sine of what? Sine of 3 times 3 squared, so sine of 27, right? Okay, cool. So here we are. All right, so obviously you need a calculator to figure out what this is. I think it's like 9 and change, but you know, just to help you like figure out if you're doing it right, but you could do that. All right, cool. Next, we have to do the speed of the particle at t equals 3. Now, in general, speed is defined as the norm or absolute value of velocity. So speed, right? Speed is equal to the absolute value of velocity, right? Okay, so that is going to be the following. I need my ruler because annoyingly I'm going to draw a square root sign with a ruler. Okay, that was nice, right? So third time was a charm. Okay, so then so we're gonna write x prime of t squared. This is always how you define speed, and then plus y prime of t squared. Now, in the interest of time, since what we have to do is do this when t is equal to 3, I'm just gonna write over these. So we put 3 in there, we put 3 in there, right? So what this amounts to is saying that what we've got is the square root of, I'll live with that. I don't want to annoy you too much. Okay, x prime of 3, well, fine, that's plugging in 3 in there. So that's, again, 9 plus sine of 27, but we must square this. So we square this, plus, and then y prime of 3, we already calculated that's the slope of this line, and that was 1/2, so 1/2 squared, that's a quarter. And so figure out what this is. This would be the speed of the particle at t equals 3. Phenomenal. Last part, right? Last part is this. Well, the last part is, hold on, sorry. So the last part is the total distance traveled by the particle. So remember, total distance is the integral of the absolute value of velocity, right? So total distance from t equals 0 to 2 is going to be the integral from 0 to 2 of the absolute value of v of t dt, right? But wait, notice that for the velocity, v of the absolute value of velocity is exactly as we just defined. So it's going to be 0 to 2, and then it's going to be the square root of, right? The square root of, and then it's, maybe that was too long. My bad. The square root of, and then it's going to be, we said x prime of t squared plus y prime of t squared, right? And then, of course, dt at the end, right? So I'm saying this here is the absolute value of velocity and its speed. We just said it. Hopefully your short-term memory wasn't so bad. All right, now, one thing that's noteworthy is y prime is not consistently the same between 0 and 2. Like y prime is this slope of this line in this part, and then it's the slope of this line. Obviously, in this part between 1 and 2, the slope is 0. So y prime of t is 0 in this part, and in this part, what is it? Rise over run would say up 2, and then to the left one, so that's -2. So that means that we have to break this integral into 2 parts. So first we go from 0 to 1, and then square root of 0 to 1, square root of, and then it's going to be and it's going to be x prime of t, that's this fellow, right? So that's not going to change. So I'm just going to write x prime of t since we all know what x prime of t is. It's this function right here, squared. And obviously you need a calculator to do this, but we said that y prime from 0 to 1 is -2. So -2 squared is 4. And so dt, and then plus, and then we go integral from 1 to 2. And again, I'm just going to write x prime instead of typing, or yeah, typing the whole function in. So x prime of t squared, and then plus, and on this part we said that y prime is 0, so 0 squared, I suppose. We could write it to make you feel good. There that is, this is a work left to your calculator, and so I am done covering your bases with a particle motion question that has to do with vectors, right? And given in vector form. All right. So finally, in conclusion, I just wanted to feel real good, even though I already corrected this in the video. So when I was doing this part, part B, in an earlier review video, I shared with you when we had to do the washer method, I misinformed you as to what little r was. So what I said is like always find little r and big R by figuring out the vertical distance from the axis of rotation. Here the axis of rotation is y equals -2, right? And what I said is find little r and big R by drawing a vertical line from the axis of rotation until you encounter the functions, right? Now, so then little r is this little fella, and then big R is this guy, right? Big R is this guy. Now, so for little r and then big R, and if you don't know what I'm talking about, R is also named the region there, so it's like the name of the region. All right, so that's poor choice, fellas. If you're gonna have us do washer, why would you name the region R? Anyway, the washer method said pi integral, and then here the limits are pretty obvious, 0 to 1, and then big R squared minus little r squared, and then dx, since we're rotating about a horizontal line. So watch that video for like a detailed solution of this. Watch the earlier review video that showed you how to solve this. But again, the only thing I want to do is correct what little r is, right? So you see the vertical distance, right? The vertical distance from the axis of rotation, I suppose I could do this in red, from the axis of rotation to the x-axis is uniformly 2. It doesn't matter where you draw it. So it's 2 there, it's 2 here, or anywhere else I draw it. But then notice that while this whole vertical distance from here to here is 2, right? While that's 2, I'll draw it in green. This little bit is a negative distance, and that's the function -2x. So whatever x this is, this vertical distance is going to be -2x. So what we need to do is do 2, the whole distance, plus -2x, which gives us this bit. In other words, 2 minus 2x. What I said was 2 minus -2x, which made it 2 plus 2x, and that's incorrect. However, so I'm saying for little r, right? For little r, we need to have 2 and then plus -2x, which is simply 2 minus 2x. Whereas for big R, we need to have, well, where was big R drawn? Right here, right? We need to have this vertical distance, which is 2, but then the output of the function for this x or any x is positive. So we need to do 2 plus this function. So for big R, it's going to be 2 plus, and then it's x e to the x squared. If I say any more, I'd be doing too much, as y'all like to say. All right, I hope you enjoyed this, and good luck on the test. Keep watching. Take care.